We'll start in 1 minute. Okay, today we'll look at some more problems in section 11.9. That's the section on functions as power series. Keep in mind that this Friday is test 4, which will be over chapter 11, sections 1 through 9. Tomorrow and Wednesday, we will review for test 4. This first problem was the one that we didn't quite finish on Friday. Find a power series representation for g of x equals 1 over x plus 1 squared. But we'll use a little bit of what we found out on Friday. If we define f of x to be negative 1 over x plus 1, then when we compute the derivative of negative 1 over x plus 1, we're going to get 1 over x plus 1 squared. But let's go ahead and compute the derivative using the quotient rule. The derivative of negative 1 is 0 times the denominator, x plus 1, minus the numerator, multiplied by the derivative of the denominator, which is 1, divided by x plus 1 squared. And this simplifies to 1 over x plus 1 squared. Okay, so if we write down the power series for negative 1 over x plus 1, and then take the derivative term by term, that will give us the power series representation for 1 over x plus 1 squared. Okay, so we've seen the power series representation for 1 over x plus 1 a few times. But here we're just taking the negative of that, negative 1 over x plus 1. So think of this as the negative of 1 over 1 plus x, which is the negative of 1 over 1 minus negative x. And then we'll take the negative of the power series expansion of 1 over 1 minus negative x. So that's 1 plus negative x to the first, plus negative x to the second, and so on. So we'll simplify a little bit inside the brackets. So the negative of the quantity in the brackets is 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. Then we'll take the negative of each of those. So we get negative 1 plus x minus x squared plus x to the third minus x to the fourth plus x to the fifth, and so on. Okay, so this is what f of x is. F of x being negative 1 over x plus 1. So now we take the derivative of f. So f prime of x will be 1 minus 2x plus 3x squared minus 4x to the third plus 5x to the fourth minus 6x to the fifth, and so on. And this is the power series for 1 over x plus 1 squared. So in the sigma notation, well, we have an alternating series. So let's start out. I'll try n equals 0, negative 1 to the n. And what are the terms? They look like n times x to the n minus 1. Let's try that out. I always have to test it. When n is 0, negative 1 to the 0 is 1. Oh, that doesn't work. So I think I should start with n equals 1 instead of n equals 0. And then change that exponent to n minus 1. So when n is 1, n minus 1 is 0, negative 1 to the 0 is 1. And 1 times x to the 1 minus 1. So that works for the first term. For the second one, yeah, it looks like that works. So this is the sigma notation for 1 over x plus 1 squared. Okay, the next example. Do you want to try this one on your own for a minute or two? So find a power series representation for f of x equals x squared over x to the fourth plus 16. So how are you starting out on this one? There may be more than one way to go about it. You want me to just do it? Okay, what I'm going to do, I'm first going to get a power series representation for 1 over x to the fourth plus 16. And then after that, I'll just multiply all of the terms by x to the second. So for 1 over x to the fourth plus 16, I'm going to write it as 1 over 16 plus x to the fourth. And then I'm going to factor out 1/16. So I get 1/16 times 1 over 1 plus x to the 4th over 16. And then 1/16 times 1 over, instead of 1 plus x to the 4th over 16, I'm going to write it as 1 minus negative x to the 4th over 16. So remember why I'm doing it that way? I want to get something that has the form 1 over 1 minus x. So I'm just replacing x with negative x to the 4th over 16, and then writing the power series representation as a geometric series. Okay, so we have 1/16 times 1 plus this term, negative x to the 4th over 16 to the 1st, plus negative x to the 4th over 16 to the 2nd, and so on. I'll write a couple more. That's probably good enough. So inside the brackets, we'll write 1 minus x to the 4th over 16 to the 1st, and then plus x to the 8th over 16 to the 2nd, and then minus x to the 12th over 16 to the 3rd, and so on. The next one would be x to the plus x to the 16th over 16 to the 4th. And we might as well distribute the 1 over 16. We could also multiply by x to the 2nd, but we'll do that in the next step. So distribute multiplication by 1/16. So we get 1/16 minus x to the 4th over 16 to the 2nd, plus x to the 8th over 16 to the 3rd, and so on. Okay, so this is equal to 1 over x to the 4th plus 16. So if we multiply this by x to the 2nd, so in other words, x to the 2nd over x to the 4th plus 16, we just multiply each of those terms by x to the 2nd. So we'll get x to the 2nd over 16 minus x to the 6th over 16 to the 2nd, plus x to the 10th over 16 to the 3rd, maybe just one more, minus x to the 14th over 16 to the 4th. And then we'll try to come up with the sigma notation for this. So how about n equals 0, and we have -1 to the n, and x to the 4n plus 2. Yeah, that looks like that's going to work. And then over 16 to the n plus 1. So does that work? Yeah, I think that one works. Yeah, on the next page, this one, use a partial fraction decomposition to find a power series representation of f of x equals 2x plus 3 over x squared plus 3x plus 2. The denominator factors nicely. So the denominator is x plus 1 times x plus 2. So our partial fractions will have the form a over x plus 1 plus b over x plus 2. And then we just want to find the values of a and b. Well, if we rewrite this sum, a over x plus 1 plus b over x plus 2, as a single rational expression with the common denominator, x plus 1 times x plus 2, we're going to get a times the quantity x plus 2, which is ax plus 2a, and then plus b times the quantity x plus 1, which is bx plus b. And this numerator, ax plus 2a plus bx plus b, has to be equal to 2x plus 3. So we can just focus on the numerator for a minute. 2x plus 3 has to equal this quantity. So 2x plus 3. And we'll combine terms. ax plus bx is the quantity a plus b times x, and then plus 2a plus b. So from this equation, the coefficient of x is 2, so a plus b is equal to 2. And 2a plus b equals 3. So it doesn't take too much effort to see that both a and b are 1. So a is 1 and b is also 1. Okay, so a power series representation for f of x is equal to the sum of two power series representations. One is 1 over x plus 1, and the other one 1 over x plus 2. We've done both of these before. Do you remember what they are? I don't, but we know how to find them. So 1 over x plus 1, we'll find the power series representation for that. Think of 1 over x plus 1 as 1 over 1 plus x, which is 1 over 1 minus negative x. And then 1 plus the term negative x to the first plus negative x to the second, and so on. So this becomes 1 minus x plus x squared minus x to the third, and so on. And then the other one, 1 over x plus 2. So think of that as 1 over 2 plus x, or 1/2 times 1 over 1 plus x squared, but 1 plus x, not 1 plus x, 1 plus x over 2, but think of 1 plus x over 2 as 1 minus negative x over 2. So we'll get 1/2 times the power series of this, which will be 1 plus negative x over 2 to the first plus negative x over 2 to the second, and so on. Okay, so we can do a couple of things at once. We can distribute multiplication by 1/2 and also change those to the alternating series. So 1/2 times 1 is 1/2. And inside the brackets, this is minus x over 2. So multiply that by 1/2, you get minus x over 4. And then plus 1/2 times x squared over 4 is x squared over 8. And then minus x to the third over 8 times 1/2 is minus x to the third over 16, and so on. Okay, so 1 over x plus 1 plus 1 over x plus 2 is the sum of 1 minus x plus x squared, and so on. And this one, 1/2 minus x over 4. So we can add these terms by combining like terms. 1 plus 1/2 is 3/2. Each of those two expansions subtract the x term. So minus x over 4 is minus 5x over 4. And both of the x squared terms have positive coefficients. So x squared plus x squared over 8, how much is that?
9x squared over 8.
Yeah, 9x squared over 8, so plus 9x squared over 8. And let's do one more, and we should be able to find the sigma notation after that. So now it's minus x to the third minus x to the third over 16. So this one is minus 17x to the third over 16, and so on. So our sigma notation we need it's an alternating series, so it's -1 to some exponent. So it looks like, well, if we focus on the denominators are just powers of 2. And each numerator in absolute value is just one more than that power of 2. So if we just make the denominator 2 to the n, if we start at n equals 1, then the numerator will be 2 to the n plus 1 times x to the n minus 1. Let's try that out. So when n is 1, n minus 1 is 0. Negative 1 to the 0 is 1. 2 to the first plus 1 is 3 over 2. And x to the 0. So it works for the first term, and it works for all of the other terms also. Okay, let's try the next one. Find the sum of each of the following series. First, we're doing this one in reverse. We're given a power series, and we're going to try to find the function for which this is a power series. So any ideas on how to start?
Just start by making a series of terms.
The which one?
Just like plugging in numbers and making a sequence.
1 over 1 minus x?
Yeah.
Yeah, let's start with 1 over 1 minus x. This is the basic one for the absolute value of x less than 1. 1 over 1 minus x is 1 plus x squared, and so on. Hey, if we take the derivative of this, so I'll refer to this as f of x. F of x equals 1 over 1 minus x. And f prime of x what's the derivative of 1 over 1 minus x?
So 1 over 1 minus x squared.
1 over 1 minus x quantity squared. Is that what you said? And then if we take the derivatives of all of the terms on the right-hand side, we get 1 plus 2x plus 3x squared plus 4x to the third, and so on. So these terms, 1 plus 2x to the first plus 3x to the second. So like an individual term in terms of n has the form n times x to the n minus 1. So if you were to write this using sigma notation, we'd get that, wouldn't we? Okay, when you compare this one, where the terms are n times x to the n minus 1, with the terms of this series up here, where the terms are n times x to the n, is there something that we can do?
Multiply every term by x.
Yeah, multiply every term on this series down here by x, and that will give us that series up there. So this series, where the terms are n times x to the n minus 1, as a rational function, it's 1 over the quantity 1 minus x squared. So if we multiply this by x, we'll multiply the individual terms also. So we get x plus 2x squared plus 3x to the third plus 4x to the fourth, and so on. So the terms are n equals, from an n equals 1 to infinity, n times x to the n. Okay, that's the one that we were looking for. So the function whose power series representation is x over 1 minus x quantity squared. Hey, do you see how the second part of this problem is related to the first part? So I'll make an even stronger hint. We can use this series and the function that it's equal to find the numerical value of this infinite series.
Does it go to 0?
Can't hear you.
I'm confused. Never mind.
Oh, you're gonna slug yourself when you see this. So n over 3 to the n is equivalent to n times the fraction 1/3 to the n.
Wait.
And then you can use the solution function from the previous problem.
Yeah.
2x to 1/3.
Yeah, so this power series is a function of x. And so when we evaluate this power series at x equals 1/3, we get a numerical value for this power series.
Yep.
So let's call this function capital F of x, say. So we just evaluate this function when x is 1/3. So capital F of x is x over 1 minus x quantity squared. So just replace x with 1/3 and do the arithmetic. So 1 minus 1/3 is 2/3. 2/3 squared. So 1/3 divided by 4/9, or 1/3 times the reciprocal of 4/9. So this simplifies to 3/4. Okay, let's move on to the next page. Evaluate the integral x divided by 1 minus x to the 8th as a power series. Any ideas on how to start? We've used a similar sort of approach already today with a different function. So let's start with finding a power series for 1 over 1 minus x to the 8th. So this has the form 1 over 1 minus x in quotes. So this will be 1 plus x to the 8th to the 1st plus x to the 8 to the 2nd, which is x to the 16th, and so on. And then x over 1 minus x to the 8th. That can be found just by multiplying each of these terms by x. So we get x plus x to the 9th plus x to the 17th, and so on. Okay, so this is the integrand of the integral. So now we integrate this power series term by term. So we'll include the constant of integration c, and then the antiderivatives of each of those terms. So x to the 2nd over 2 plus x to the 10th over 10, and so on, plus x to the 18th over 18. So c plus power series so x to the 8n plus 2 over 8n plus 2. I think that works. Yeah, that appears to work. So that didn't take too long. Okay, now find a power series representation for f of x equals the natural log of 1 plus x.
Can you start by taking the derivative and finding
Take the derivative.
so? I'm not sure.
Yeah, what's the derivative of the natural log of 1 over 1 plus x?
I think it's 1 over 1 plus x.
Yeah, 1 over 1 plus x. We've seen that before. So 1 over 1 plus x, think of that as 1 over 1 minus negative x. So we get 1 plus negative x to the first plus negative x to the second, and so on. So we get a alternating series, 1 minus x plus x squared minus x to the third plus x to the fourth, and so on.
And do we just integrate those terms?
Yeah, now to find the power series for the natural log of 1 plus x, we just compute the integral of this. So we'll include the constant of integration c, and then write antiderivatives for all of those terms. So plus x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. So the sigma notation then, I guess we can start with n equals 1. It's alternating. So x to the n over n. Hey, we can find the value of c. See how to find or to determine what the value of c has to be in this case? Well, when x equals 0, we get the natural log of 1 plus 0, or the natural log of 1, which is equal to c plus 0, because each of those terms in the series has x in it. But the natural log of 1 is 0. So 0 equals c plus 0, so c has to be 0. Okay, so the power series representation for the natural log of 1 plus x is just the series. while we're at it, what's the interval of convergence? So if we recall the ratio test, so x to the n plus 1 over n plus 1 divided by x to the n over n, which is the same as x to the n plus 1 over n plus 1 multiplied by the reciprocal of that, n over x to the n. So this becomes n over n plus 1 times the absolute value of x. So when we take the limit of that as n approaches infinity, and we want it to be less than 1 so that it converges, right?
So that goes to 1 times the absolute value of x.
Yeah, this limit is the absolute value of x, which has to be less than 1 if the series converges. And so the radius of convergence is 1. And negative 1 is less than x, which is less than positive 1. And then to check the endpoints, well, when x is positive 1, we just get the alternating harmonic series. So when we test x equals 1, we get convergence because the alternating harmonic series converges. When we test the other endpoint, test x equals negative 1, so notice what happens when x is negative 1. We have negative 1 to the n minus 1 times negative 1 to the n. So all of the terms are negative. And the negative of the harmonic series diverges because the harmonic series diverges. Okay, so the interval of convergence then is so parenthesis, oh, can't see. So the interval of convergence is parenthesis negative 1, comma 1 bracket. Okay, we have a few minutes left. We can use what we found for this next problem. So let's recall what the natural log of 1 plus x is. So that's this series. Okay. So evaluate the integral x squared times the natural log of 1 plus x dx. So all we have to do is multiply the power series of the natural log of 1 plus x by x squared. and then integrate term by term. So x squared times the natural log of 1 plus x is x to the third minus x to the fourth over 2 plus x to the fifth over 3, and so on. And then you can find the antiderivatives of each of those terms. Okay, but I wanted to get to this last problem. Find a power series that is equal to the natural log of 2. So we don't need that much space. Since the natural log of 1 plus x is equal to this power series, and the interval of convergence is from -1 to +1, including +1, then the natural log of 2 is the natural log of this with x replaced with 1. Sorry, this is... Okay. So that's all we have time for today. Tomorrow we'll do the test 4 review.